Chapter 4, Section 8, Continuous Culture. Now, in the previous sections, talked about closed systems, closed cultures. You transfer over to a tube, you seal the tube, you let things grow as is. Well, that's great if you want limited numbers. Here's my end point. Here's what I'm growing it up to this point, and then I'm done. But sometimes you want to do what is referred to as an open system, a continuous culture. You start this culture growing, and you're continuously adding in fresh broth. You're removing some of the waste products as it's going so that the culture never hits the stationary. It just keeps going and going and going. There's no decline. There's no death phase. Commonly do this with what is referred to as a chemostat. If you're working in industry, certain microbes you want to keep going because they have been genetically modified to express certain proteins or to make certain things that need to be extracted. Well, you'll use a chemostat, so that way you're not starting a new culture every day. You start one culture and you just let that one go for weeks. Start another one tomorrow, let that one go for weeks as you're continuously removing from that culture, and it's continuously going. It's in a steady state. So you're adding in fresh media all the time. There's an overflow so that waste products can be removed. And in this waste product, there's going to be some of the microbial cells. If you need to pull some of them out so that they can, certain proteins can be extracted from them. Or maybe the cells are, excreting certain compounds. Well, the bacteria continuously growing in here, new stuff coming in, keep them happy. They're excreting out into the liquid certain compounds. Well, you can pull off the liquid. And then at a later point, remove from that liquid, that liquid broth, the excreted compounds that you need for your pharmaceutical company or whatnot. You have to take into account certain things when you're using these chemostats. Well, that growth rate that I talked about last section comes into play here. You want to get this balance where this growth rate, while it's maximized, it's not, I'm sorry, the growth rate is such you're not going at the max because then you will overgrow the capabilities of that chemostat too quickly, and then you'll have to start over. So if you come up with ways, instead of having a nice sharp growth of the growth rate, but then you shallow it out a bit so that instead of within 12 hours you hit maximal, your number maximal, you shallow it out. So now instead of 12 hours, it's over a few days until you hit a certain biomass yield. Here's the maximum number of cells that can be handled in that chemostat. You take into account dilution rate. How much new media has to be added to maintain this biomass? How do we maintain this biomass without exceeding the limits of the chemostat and without overwhelming our culture, which will then trigger that decline, that death phase? Because if you go too fast on the growth rate, you could hit this maximal biomass. Hit that maximal biomass and then boom, everything just drops. So you can use limiting nutrients. Boom, 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 boom. Limit certain nutrients, bring the growth rates down, and then your maximal biomass or whatever can be maintained longer. its nutrients are going to be your limiting factor. Here's the variable you get to play with. You know, of that new broth being added, which of the nutrients there, what concentrations are you going to play with? Are you going to, artificially lower so that you can maximize your yield? That's the key point here. Maximizing yield of bacterial cells made and can be maintained, or maximal cells there that are then going to maximally produce your genetically modified protein of interest or whatever. So you can put these cultures into the exponential growth phase and then maintain them there for weeks, if not months. I keep referring to, industry, but, there's been published research where this is how they study the physiology of certain microbes. Put them into this exponential growth phase for weeks, months, and it gives them a means for going in and studying what's occurring, in the presence of X, in the presence or absence of Y. How does this change physiology? Microbial ecology. You can put in different species of bacteria and see how that affects growth patterns, see how that affects numbers, see how that affects gene expression.